So, few more things regarding current and voltage. First of all, about current. And before even that, some symbols that use in when we draw electrical circuits. Some symbols. First symbol is this. That means cell or battery. Can be like this, or can be few of them shown together. I will be using just one. It's a battery or cell. Of batteries, few cells connected together, where long line represent positive terminal and short line negative terminal. Another symbol that we will be using, two other symbols we will use. Symbol like this, that is switch. So that's battery, switch, which can close the circuit or open circuit. So you turn on, turn off. Close it, you open it. Now, globe. There are two ways how we can show them. One way is like circle with a such cross inside, or another way we can do like this. They can be used any of them. There's no difference. You can use this symbol, you can use this symbol. Like that.
What does it do?
Another symbol that we will be using, it's again two versions, same thing. They're completely interchangeable. It's a resistor. What is a resistor and what it does a little bit later on. Either this or this, they're equivalent, no difference. Some books using this symbol, some using this symbol. So it doesn't matter if you see any of them, it's the same thing. And also, those will be some measurement devices. What do you think this will mean? Ampere meter, which measure amps. Ammeter, it measures current, and this one, voltmeter, which measures volts, measure voltage. Meter, voltmeter. Later on we will be adding some more symbols, so that's enough for now. And just the lines, they means connecting wires. Just connecting wires. So let's consider the simple, very simple electric circuit. We have a power source battery. We have a switch. And we have a light bulb. And we will add, no, we will not add, we will add ammeter later. So very simple electric circuit. By the way, from the next week, we will start doing quite a few tracks where we will be connecting circuits, doing measurements, and so we will have a lot of hands-on things happening. So this is the simplest, very simple circuit. Battery, switch, and light bulb. So when switch is open, will be globe on. No, there is no way for the charges to pass through. The circuit is broken, it's open. To get current started, we need to close it. And we were talking that we're looking at this stage at least only the current in the metals. And we discuss which charges are moving when we have a current flowing through the metal. Which charges are moving? Electrons. What charge electrons have? Positive or negative? Negative. So if we have positive terminal, negative terminal, how electron will be moving? Where will be getting from?
They move from negative through the switch and light moving to positive.
Yep. Electron, if we close the switch, so make the circuit complete, we'll have electrons, they will move around the circle and return to positive terminal. And then battery push them, that's power source, provide energy, it again will push electrons through, and that's how they will go. Makes sense that electrons will move this way. But what we will be considering as direction of the current is what's called conventional current. And direction of the conventional current is taken from positive to negative. So that's what will be taken as a direction of the current. So we will take direction, it's a convention, that take direction of the current from positive terminal, from plus to minus. Even if the actual, Yona, can you please close the door? Thank you. And even if you know that the actual electrons, they move from negative to positive, but we take conventional direction from plus to minus. So that's the conventional current. Now current can be two types. We can have DC current. DC stands for direct current. Direct current, which has same direction. If we have battery, it always have plus positive terminal on one side, negative on another side, and current will flow all the time in the same direction. And if it's battery, if it's providing same voltage all the time, it will provide the same current. So if you will sketch the graph of the current against time, it will look like this. It's always in the same direction, and this is not just DC, it's constant DC. All the time, battery provides all the time same, until it becomes flat. It provides, let's say, 1.5 volt, and so the current will be all the time the same. Makes sense what is direct current? But the current that comes in from the power point, where you connect the device, the current coming from there is not direct current. That current is called AC current. AC, alternating. That means it changes its direction all the time. So current that comes in from the power point looks like this. It changes direction all the time. It's flowing one direction, then opposite. Forward, backward, forward, backward, forward, backward. And that AC current. Why is that? Because when electricity is produced at the power plants, like naturally it's produced AC. How the electricity is produced, it's a part of the unit 3. How this AC current is produced on the power plant. That we'll learn later on down the track. But that's how it changes. So it's flowing one direction, other direction. And how many, the number of the cycles, that will be one cycle. That is one cycle, flowing one direction, then back. That's one cycle. Number of these cycles per second, you say it's frequency of the current. Do you know what is the frequency of the current in Australia? In Australian power points? 240, it is voltage. Current is 50 hertz. The frequency of the what is hertz, actually we'll know a little bit later on, but current in Australia 50 hertz. That means in 1 second there are 50 such cycles. In 1 second it's 50 times, so in one direction then backwards, and 50 times every second.
So
50 hertz.
So that is 1 hertz. One cycle is 1 hertz.
One cycle in 1 second will be 1 hertz.
Oh.
50 cycles in 1 second, 50 hertz.
Oh.
If it will be 1,000 cycles in 1 second, it will be 1,000 or 1 kilohertz. Yes?
So what is the different like hertz, like what's the frequency, how does it affect the electricity? If there's a higher or lower frequency, what does that mean?
Why it's choosing 50 hertz? Many countries, I will say probably a significant number of countries using 50 hertz. For the current, some using 60 hertz. To be honest, I don't know the answer, because I'm saying some using 50, some using 60, why that was chosen. And if this is the best or not. In America it's 60 hertz, and say in Europe, Australia it's 50 hertz. What is better? Can't tell you. Don't know. But where was the point made about the voltage? That the voltage in Australian power point is 240 volts. But it's changing all the time. So if you look, the current changing like this, the voltage will be changing exactly like this. Will be same. Voltage against time changing like this. Where will be 240 volts? Will it be maximum? No.
Yeah.
It is not. 240 volts will be here. And that call, later on we will get more into it, but that called RMS, voltage RMS, and it's equal to 240 volts in Australian power point. RMS, for now, it will be enough for you that it's like sort of average. Later on, we look in more detail why. And the relation with the peak, that is the peak voltage. The maximum voltage is the peak voltage, and the relationship between them, that the peak voltage, peak equal root 2 times voltage RMS. Root 2 times voltage RMS. So if you use a calculator and you calculate what will be peak, you multiply root 2 times 240, you will get 339 volts. So at peak, voltage reach in Australia 339 volts, but we're talking 240. Why is that? Let's see it later on. By the way, it's a very good mathematical question to derive this relationship, and you don't have mathematical tools at the moment, even for doing methods 1, 2. You don't have enough tools, mathematical tools to do it, to be able to do it. Who will be doing specialist mathematics, doing unit 3, when you will be doing 3, 4, will be able to do that mathematically. Okay, that a little bit more about the current. Any questions so far? So we learned about the current can be DC and AC, and direction, conventional current. Yes?
What does RMS stand for?
Root mean square. Now, EMF. What is EMF? In some questions, you've seen EMF. And EMF is abbreviation of electromotive force. It pretty much has nothing to do with the force, so it will confuse the name EMF, but what is EMF? It's a voltage. It's a voltage. But we use what's EMF when we're saying about the voltage provided by power source. So we don't say, let's say, EMF across the globe. We say voltage across the globe. But EMF, when we say voltage provided by the battery, we still can say voltage, but we can say EMF. Let's say EMF of the battery equal 1.5 volts. And we can say voltage provided by the battery is 1 volt. It will be the same thing. So EMF, it's used for the voltage provided by the power source. So that's what EMF stands for. So if the equation is EMF, that means power source provides that voltage. It's no difference to voltage. You can say battery provides 1.5 volts voltage, or it provides EMF 1.5. But we cannot use, we're not using EMF to say that EMF across light bulb. No. They will be corrected to say voltage across. For battery, we can say both. EMF is 1.5 or voltage is 1.5. Make sense? Okay, now, we learned what is current, what is voltage. Let's see how they are related. What do you think will happen with the current? So we have connected one battery, one AA battery, provide 1.5 volts. And we measured some current in the circuit. But then we, instead of 1.5, we connected two of them, and now we have 3 volts. What will happen with the current through the circuit? Okay. What will, yes?
The electron will
There will be more current, there will be more electrons. So if we increase voltage, it's pretty much quite obvious that it will be more current. So voltage, current will be proportional to voltage. The more voltage we apply, the bigger will be current. Now, what will determine how much current will go through? We might put one globe, you get one current. For the same voltage, can another one, and will be another current. And that's where we need to introduce one more physics quantity called resistance. Resistance. And we denote it with letter R. Can be capital, can be lowercase r. Doesn't matter. R is resistance. It's measured in ohms. So resistance, unit for resistance is 1 ohm. Again, it's a synonym of the physicist, ohm. But usually we write 1 ohm is traditionally written Greek letter omega, like a sort of a circle with the 2 legs. That's how we will be, and on your diagram in the textbook, the ohm is written. That's the unit for resistance. And resistance tells us how easy electric current gets through something. So what do you think? If you take piece of metal and you take piece of plastic, where current will be easier to get through metal or through plastic? Metal. So which will have more resistance to the current? Plastic will have more resistance. So resistance, the bigger resistance, the harder for current to get through. The smaller resistance, the easier for current to get through. And relationship between voltage, current and resistance is described by the Ohm's law, which pretty much is represented on my t-shirt. And the formula is that current equal voltage divided by resistance. That's called Ohm's law.
Is this all in our book, so we don't have to write it down?
Hmm?
Is this all in our book, so we don't have to write it down?
Yes, it's all in, it is in your textbook, it is in your booklet as well. So that is Ohm's law, I equal V over R. So the higher the voltage, if we increase voltage, what will happen with the current? There will be more current, bigger voltage, bigger current. With the resistance, if we make bigger resistance, what happens to the current? Smaller current. So voltage bigger, current bigger, resistance bigger, current smaller. Make sense?
Yes.
That is Ohm's law, and one more last thing, how we measure current and voltage. No, just give you an example. Let's say battery provides 1.5 volts, voltage equal 1.5 volts, and current through the globe, let's say current is 200 milliamps. Question is, what is resistance? What is the resistance? How we can look at it? We need to rearrange that formula. And to make it easier, we can write it for people who have some difficulties with this algebraic manipulations. We can write this formula in this form. V I R. So if we, what we're looking for? What we're looking for? Resistance. So we cover resistance. What resistance equal? Voltage over current, so equal 1.5 divided. But what we should put instead of current? We cannot put milliamps.
0.2.
That is, will be 0.2. Because to turn into the amps, milli means 1,000th. So we divide it by 1,000, will be 0.2. And will be equal,
7.5.
good, calculation skill, 7.5 ohms. Make sense?
Yeah.
Now, if we make a simple circuit and connect resistor with resistance R, and we want to measure current through, by the way, when we say voltage, we should say voltage across, because voltage always between 2 points, voltage across, but current through. So we need to measure current. What we need? Add to our circuit a meter. To measure current, we add a meter, And to measure voltage, we need to add voltmeter. Now, how we add? Ammeter, we add like this, before or after the resistor in series. Why we do that? Because we want ammeter, because what ammeter does, in fact, it's sort of count all electrons coming through. So we need to make sure that every single electron will get through ammeter. So that's how we connect ammeters. And that's called in series. We connect ammeter, we say in series. And the resistance of ammeter is approximately 0. Very, very little. Why we should have resistance of a meter very, very small? Why? What do you think? Yes.
So that all the electrons can get through, so you can measure it.
Mhm. Any other? Thoughts? Yes.
Maybe so it doesn't alter the circuit as much.
That it will not affect the current, because if it will have more resistance, as they will be harder for electrons to get through, and it will affect the circuit. So that's why ammeter has very, very little resistance, close to 0. Now voltage we measure across. So how we need to connect voltmeter? We connect voltmeter across. Because we want to measure voltage between 2 points. And that's called in parallel. And the resistance of the voltmeter ideally it should be infinite. In reality it's not, but approximately we'll consider that it's infinite. Why we want? Because we don't want any electron don't move through here and turn there. So voltmeter requires very big resistance to not affect the current. And when you will be connecting circuits, doing your measurements, please make a note, remember. Because if you will connect a meter like this, what will happen?
They'll go through the meter instead of.
It will burn, it just burns out. If you connect a meter, like if you connect voltmeter like this, nothing happens, you just will not have any, or almost no current through the circuit. But if you connect a meter like that, then the meter will burn. So that's how you connect ammeters and voltmeters. Any questions? Okay.